Today we're going to take what we learned last class on parametric equations and move into the calculus realm. So we're going to talk about some calculus things that need to be done with parametric equations, and this is a lot of stuff we did in first semester. So hopefully this will be some review of things that you learned in first semester, specifically about derivatives, horizontal and vertical tangent lines. And then also we're going to jump ahead to something we did this semester, which is length of curves in parametric form. So a lot of formulas in here. We're going to box in the important stuff. So if we have a curve C that is given by two parametric equations, remember parametric is one where you have x's and t's and then y's and t's. The slope is given by this equation right here. So if you would box this in, if you are finding the derivative of a parametric equation set, well, it's two equations, and you're trying to find the slope, and slope is defined as dy dx. Well, y and x are two separate equations. So what we have to do is we have to take the derivative of the y equation that has t's in it, and also take the derivative of the x equation that has t's in it, and make a ratio out of it, dy dt over dx dt. That gives us the derivative. Now, note that this formula is in terms of t and not x. So in other words, when you finish finding the derivative, it's going to be dy dx equals blah, blah, blah with a t in it, which is kind of weird because there's no t in dy or dx, and that's okay. So what it goes on to say is to find the slope of the tangent line at a parametric point. If they give you a point x and y and your equation's got t's in it, you've got to find the t's that correspond with that x and y, okay? Now, when we do this, when we do a problem, it'll make a lot more sense. So, a couple other things you need to know. The curve has a horizontal slope if dy dt is 0. Now, if you think about it, horizontal lines are y equals lines. So it's dy dt that must be 0 in order to be a horizontal. And the curve has a vertical slope or a vertical tangent line when dx dt is 0. You've just got to memorize that. But it really kind of makes sense. Vertical lines are x equals, so dx dt must be 0. Now the other thing you need to notice, it says dy dt is 0, for example, but dx dt can't be 0. They can't both be 0, because that's a 0 over 0 situation. All right, so we've got to be specifically looking at one or the other. So what we're going to do is we're going to find dy dx for the curve given by these two parametric equations. First at t equals pi over 3, then at the point 1, 0, and then at the point 0, negative 1. So first thing we've got to do is find the derivative. But in order to do that, we need the derivative of each of these with respect to t. So on top of it, just to save some room, after this I'm going to do it underneath. They didn't leave a big space for this problem. What is the derivative, dx dt, of that x equation?
Negative sign.
Negative sine of t. And what is the derivative of the y equation? Negative cosine of t. Okay, so now we're ready to go. So first you take the derivative of each one individually, then we come out to the side and we write that dy dx is equal to the y1 over the x1. That's why it's dy over dx. So we take the dy dt equation and put it on top. We take the dx dt equation and put it on the bottom and clean it up.
No.
So what is negative cosine over negative sine simplify to be?
Cotangent.
Positive cotangent. Very good. So our derivative for this problem is cotangent of t. Okay? So we need that for all three parts, A, B, and C. So I'm going to box that in. Now down here I'm going to do A. A takes the least amount of space, so I'm going to do it right underneath here. I need the derivative at t equals pi over 3. Since they gave me a t value, I just need to plug it in. That's all I need to do. So let's review the notation. We write dy dx with a line, and then at the bottom write down what we're plugging in. T equals pi over 3 equals. So we write dy dx line t equals pi over 3 equals, because they're all three different variables here. So now all I do, since it is a t value, is plug it in. So I have cotangent of pi over 3 And think about the unit circle. What is the cotangent? Pi over 3. Cotangent, remember, is x over y. Pi over 3. 1/2 over root 3 over 2, which is 1 over root 3. The 2's cancel out. So this ends up being root 3 over 3. And there's my first answer. It says now I want the slope at the point 1, 0. Okay? What letter is 1? X. What letter is 0? Y. Is there a place to plug an X or a Y into my slope? No. It's all T's. I don't have no place to plug it in right now. So what I need to do is find the T that works in both equations. So what I'm going to do is take my two regular equations, not the derivatives, but the regular equations, plug in 1 for the X and 0 for the Y, and find the T that they have in common. So watch this. We're going to write 1 equals cosine of T, and 0 equals negative sine of T. And I'm going to draw a little bird beak thing right there. So tell me, where does cosine equal 1 and sine equals 0?
2 pi.
0 or 2 pi, but let's stick with the simplest one, which in this case would be t equals 0. Okay? So I had to find the t that works in both equations at the same time. And that is now the t I'm going to plug into my derivative. So I write dy dx with my line and t equals 0 equals. We plug 0 into the cotangent. We end up with cotangent of 0. 0 is x over y. Well, guess what? They already gave me my x and y. 1, 0. What is 1 over 0?
Undefined.
Undefined. Very good. There's my second answer. Do you have any questions to this point? Are you seeing the process that we're going through? Okay, letter C is the point 0, -1. Okay, what was the first thing I did on the previous problem?
You start with where the points make sense.
Yes, we plug the two values in, x and y, into their respective parametric equations. So we have 0 equals cosine of t, and -1 equals negative sine of t. Now, just to make things a little clearer, let's change the double negative to a positive. So, where does cosine equal 0 and sine equal 1?
3 pi over 2.
Not a 3 pi over 2, where sine equals positive 1s.
Oh, pi over 2.
Pi over 2, there you go. So t is this time pi over 2. Because remember, the y equation is negative sine. So now we do the same thing again. We do dy dx with our line t equals pi over 2. And we end up with cotangent of pi over 2. And remember, cotangent is x over y. And our x is here and our y is here. So 0 and 1. What's the cotangent at pi over 2 then? What's 0 over 1?
0.
Be brave. It is 0. It is 0. Okay. Questions? Are we good so far?
So far.
So far, so good. Not so bad. Okay. Now we're going to talk about how to do a second derivative or a third derivative given this format. Now, let's review real quickly. Forget what's on the paper. Just think. Y equals x to the 4th. What is the first derivative? 4x to the 3rd. Agreed? What is the second derivative? 12x squared, right? You bring the 3 down, multiply it to the 4, 12x squared. So basically it's just taking the derivative of the derivative, right? But because we have two equations involved, it's a little more complicated here. This, remember, means second derivative. This is saying the derivative of the first derivative. And look what it tells you to do. It says take the derivative of your dy dx, but then divide it by dx dt, which is kind of a strange thing to do, but this is what makes it work. So box this in, please. And box the next one in. So what you have to remember is that once you find the first derivative, you can't just take the derivative of it to get the second derivative. You got to take the derivative of it and also divide by dx dt. So I'm going to write a note out to the side. Always remember to divide by dx dt. Not dx dt factorial, just dx dt, exclamation point. We're done with factorial for a while. Thank goodness. All right, so number 2 says, find the second derivative for the curve given by the two same parametric equations as the top at t equals pi over 3 and at the point 0, -1. All right? So let's first of all copy down what the first derivative was. dy dx was the first derivative, which was cotangent of t. Agreed? Now we're going to take the second derivative. So this will be d squared y over dx squared equals. Now, based on the formula that I have boxed in right here, I need to take the derivative of the derivative with respect to t. So what is the derivative of cotangent?
Oh,
Negative cosecant squared. So that is the top of my fraction, negative cosecant squared of t. So I took the derivative of my derivative, got that, but now I must divide by dx dt. Now go back to the problem we did before. What was dx dt? Look at number 1. What was dx dt that we wrote down? Negative sine of t. That has to go on the bottom. So the top is the derivative of this. The bottom is dx dt. And if I was to do it again, after I clean this up, the top would be this, and the bottom would be dx dt. And if I did it again, the top would be that answer, and the bottom would be dx dt. Are you getting the point? I keep doing dx dt every time. All right? So let's clean this up. First of all, what sign is it going to be? Positive. And cosecant is the reciprocal of which trig function? Sine. So if I move the cosecants to the bottom, I'm going to have how many sines down there? Try again. I'm going to have 3. I have 2 and already 1 down there. So this is going to be a positive 1 over sine to the third of t. 1 over sine cubed of t. That's my second derivative. Okay, now I could write that as cosecant cubed. Somebody asked me last period, it was a good question. Well, why don't you just write it as cosecant cubed? The reason being, it's much easier to plug stuff into a sine than it is to plug it into a cosecant. Do you agree with that statement? So even though that's uglier, it's much easier to work, because I'd have to change it back to sine to plug it in anyway. Okay, so part A, I'm going to box this off, get it out of the way. Part A says I want d squared y over dx squared line t equals pi over 3 equals. So, do I have to make any modifications, or can I plug in the pi over 3 right now? What do you think? My equation has t's in it. What they're asking me to plug in is a t value. So in it goes. It's ready to go. So this would be 1 over sine of pi over 3 cubed. Right? That's the same thing. All right. What is the sine of pi over 3? It is root 3 over 2. So I'm going to have 1 over the square root of 3 over 2 cubed. And so to take that off the bottom, I need to flip it when I move it up. So I'm going to give the power of 3 to both of these. So it would be 2 to the third on top and the square root of 3 to the third on the bottom. Agreed? Now as far as AP goes, you can stop there. You could have stopped the step before if you wanted to. They do not require cleanup. But if you want to make your answer match the one on the back, when you do problems, you need to know how to clean it up a little bit. Okay? So what is 2 to the third? 8. Now what is 3 to the third? 27. So when you break down the square root of 27, that would break into 9 and 3, right? And square root of 9 is what? 3. So we have a 3 outside and a 3 left inside. Do you agree with that statement? So this is going to be 3 root 3, and that's done. That is as simplified as you need to go. No rationalizing denominators. Don't have to do that anymore. You guys are special. You're beyond pre-cal. Okay? Questions? All right, that was kind of long, but the next one's easy, promise. So, when we do part B at the point 0, -1, we already figured out what the t was. Go back up and look at letter C on number 1. What was the t value there? Pi over 2. So I don't need to do that work again. So we do d squared y over dx squared at t equals pi over 2. So we just take our derivative, plug in pi over 2. So now it's sine of pi over 2 cubed this time. Not square root of 2 over 2, that's pi over 4. 1. It's just 1. So 1 over 1 cubed is 1. We're done. Questions on that? Are you following along? Doing okay? Y'all are very quiet, but that's okay. We are going to skip number 3. Now let's go to the back. Look at the top of the back of the first page, and there's our loop-de-loop question from the other day. Remember our loop-de-loop question that we graphed? We're going to find out some information about this loop-de-loop graph. Now, and they were nice. I think this was actually an error on their part, but that's okay. We have the cycloid based on these two parametric equations. T is greater than or equal to 0, and it's over here to the right. Find the derivative. Well, they already did it for us. So thank you very much. They already did the derivative for us, but we're going to answer the rest of the questions, okay? The question says, first of all, what's the equation of the tangent line? Oh, we haven't seen that in a long time. Okay, that's what I want somebody to say a little bit. Say it a little bit louder for me. How does it go?
Y. Is it y1?
No, it's just y.
Y minus blank equals blank times x minus blank.
Okay, write this down. Make your blanks a little long because what we're putting in them is going to be a little longer than one term. So remember that when we do equation of tangent line, that's the first thing you write down right there. Y minus blank equals blank, x minus blank. Okay, so we have the equation of the tangent line at t equals pi over 4. Well, is there any place, do any of those blanks require a t? No. So the t is there. It's going to help us find everything, but it doesn't go anywhere in the equation. So let's start where we usually start, which is back here. What goes in this blank here? An x value, okay? Is there somewhere on this page a relationship between x and t?
Yes.
Where is it?
The derivative?
Right there. I have not in the derivative. There is one in the derivative, but I want a straight x and a straight t. That's this first equation. So I'm going to plug the t in here to find my x value. Does that make sense? If I plug in t, I'll get x, and then I can put it in the equation. So x equals t, which is pi over 4, minus 2 sine pi over 4. So pi over 4 minus 2 sine pi over 4. So what is the sine of pi over 4?
2.
Square root of 2 over 2. So I'm going to go ahead and save myself some paper, and I'm going to write it up here, square root of 2 over 2. So pi over 4 stays pi over 4, minus, how does 2 square root of 2 over 2 reduce? Just root 2, without any denominator. So that is my x. So that x needs to go in the x blank. Pi over 4 minus root 2 in a parentheses. Very important that it goes in a parentheses, because it's got two terms in it and it's minus in front of it. What goes in the first blank? Y. Is there a way to find what y is? Yes. Where is it? Y equals. Okay, so let's do that one. Y equals 2 minus 2 cosine pi over 4 equals. Now once again, I know cosine of pi, well wait a minute, maybe I don't know. What's cosine of pi over 4? Root 2 over 2. So 2 times root 2 over 2 is going to be, it's going to be 2 minus root 2. Agreed?
Yes.
So that goes in the first blank, in a parentheses. 2 minus root 2. There it goes. All right. We're cooking right along. So, what goes in the middle blank?
The dydx.
The slope. Do we have an equation for that?
Yes.
Yes, we do. So we plug in those values. So we're going to have, and I'm kind of running into the other part of my paper. I'm going to have to go up here. So I'm going to do 2 sine pi over 4 over 1 minus 2 cosine pi over 4. Okay, we already know the sine of pi over 4 and the cosine of pi over 4. So sine and cosine are both square root of 2 over 2. So it's just going to be square root of 2 on top. And then 1 minus square root of 2 on the bottom. Agreed? So let's put that little fraction guy in the last blank. Square root of 2 over 1 minus the square root of 2. Parentheses, not necessary, but okay. And we have now built our equation of our tangent line. Wasn't very hard, was it?
No.
Just had to know where everything goes and how to find stuff. So, letter C. The values of t where the curve is horizontal. What do we set equal to 0? dy dt or dx dt? Horizontal. It is dy dt. Okay? Now, I don't see dy dt on my paper, but it's here. It's here hidden in the derivative. Which part of the derivative is dy dt, the top or the bottom? The top is. So I'm going to write an equals dy dt out to the side for reference, and then an equals dx dt out to the side of the other one for the reference. So now I need dy dt, don't I? I'm supposed to set it equal to 0, because I want the slope to be 0. So 2 sine t equals 0, and here's where more of your trig skills come into play. We've got to solve the equation. How do we do that? Divide by 2. Sine of t equals 0.
So at 0.
At 0 and pi and 2 pi and 3 pi and 4 pi and 5 pi. So we just do dot 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 because we got a pattern going. Okay? Now remember that the statement said there's a horizontal tangent as long as dy dt equals 0, but dx dt doesn't. Okay? So let's test ourselves here. If I plug a 0 into the bottom, am I going to get 0 here? No. So all of these answers are fine. They're going to be fine. So the values of t where the curve is horizontal are right there. Let me go ahead and write out to the side here for reminder. This is where dy dt equals 0. If we do the vertical, that's where we set what equal to 0? Dx dt. So that's for later when I'm studying, to remind myself where did I get this stuff from. Dx dt is 0. When the curve is vertical. So dx dt is the denominator. 1 minus 2 cosine of t equals 0 minus 1. So negative 2 cosine t equals negative 1.
You make those
Pardon me?
you make them positive.
Yes, and also do what?
Divide by 2.
Divide by 2. So I'll basically just divide by negative 2, which will take care of that. So cosine of t equals 1/2. Where does that happen? Careful. It's pi over 3 for sure. And what other quadrant do I have positive x values?
Fourth, it's
The fourth.
5 pi.
That's 5 pi over 3. Okay. Now, I can't do a dot, dot, dot yet. I did that first period, and I now wish I hadn't. I need to show that I'm going around the circle multiple times. What is this one here if I've gone around more than once? It is 7 pi over 3. And as long as you've gone out one more, you show that you're going around the circle that many times. So 1 pi over 3, 5 pi over 3, 7 pi over 3, dot, dot, dot. You probably last year in pre-cal had to write the 2k pi format. Do y'all remember that?
Yes, that was
Yeah, that's nice, but it's not necessary. You can write it with dot, dot, dot. Okay? Now, these answers are totally different than these answers, so we know that these answers are good. I didn't box in my dot, dot, dot. That was horrible. I messed it up.
Oh, so now we do that.
Yes, now we do it as long as we've gone out 3 to show that it's not a perfect every 4 like a series. It's around the circle. You could do pi over 3 plus 2k pi, 5 pi over 3 plus 2k pi, and then you don't have to think about it. Steven,
One of those whole constants again.
we are finding on this loop-de-loop where the vertical tangents are going to be. Okay? And we're finding on this part where the loop-de-loop where the horizontal tangents are going to be. Okay? Because every parametric equation makes a normal looking graph. But we have to use those equations, either combine them together like we did last class, eliminate the parameter, but in this case that would be impossible. So it's easier to find the horizontal and vertical tangents in the way they are. Okay? Any other questions? Are we good? Awesome. All right, we can jump down now into talking about arc length. Arc length, big star. We got one more formula to learn. There's a lot of stuff in here, and he derives everything, but we're going to jump to the end. It's like reading the end of the book. Here is the formula for arc length of parametric equations. Now, the arc length formula before was the integral of the square root of 1 plus the derivative squared. Now, I will tell you that I've worked through this whole assignment myself, and the number one mistake I made every single time was forgetting the square root sign. You know to square the dx dt and the dy dt, but don't forget the square root sign, because it's going to throw your answer off. All right? I will show you when you put it in the calculator what to look for, because remember how everything scrolls off the page? You're like, wait a minute, did I put a square root or not? The bar will continue across the top of your calculator if it's there, so you can check it. All right. This will all be done on the calculator. That's why I had you get calculators out. So let's take a look at this. It says to find the arc length of the parametric equations. So, in order to find the arc length, I need dx dt and dy dt. So let's do that first. Underneath here, write down dx dt equals. And I want you to take the derivative of that. What's it going to be? Very simple. 1 minus, careful, what's the derivative of t squared? 2t. So this is just 1 minus 2t. Agreed? And then dy dt is equal to power rule. 3t to the 1/2 power. So, arc length L equals integral. What are my limits of integration? 0 to 2. Big square root sign. First, dx dt in a parentheses, squared. Plus dy dt in a parentheses, squared. dt on the end. type it in your calculator. Okay, if your calculator is still set from yesterday, it's already still in T's. Now, if it's not, you can type it in X's, it doesn't matter. You'll get the same answer either way. So, clear this out. So we have Math 9, our favorite friend, 0 to 2. Square root first, then a parentheses. Not a comma, parentheses there. So 1 minus 2t, parentheses squared. Oh, I'm down so low. Didn't know that. Plus, parentheses, 3t, up arrow, 1/2. Come down, close your parentheses, squared. Move over, dt. And the winner is 6.291. Do we all agree with that answer? Yes. So L equals 6.291 or 292. It does not matter. Round or truncate. That's how long the arc length would be. Any questions? Any calculator issues? All right, let's move to the next one. I want you to do this one. Find dx dt, and then find dy dt, and then do the limit, the arc length, and do your integral right now. You can do those derivatives, they're very easy. So let's go ahead and put this in the calculator.
I just got it.
Okay, good. So we're going to move this over. We have Math 9. Hello, turn on calculator. Math 9, 1 to e, square root, parentheses 1 over t squared, plus e to the 2t. That's the same thing. E to the t to the second is e to the 2t.
12.51.
Let's see. 12.506. Yay! We love it when we get the same answer, right? Any questions on this problem right here? Are we good on this? So we can do arc length. 506 or 507, either one. Okay? We are going to skip number 6, and we are going to move on to the back. Do some application problems. We're going to look at 7 and 8 specifically. We have a circle of radius 1 rolling around the circumference of a larger circle of radius 5. The epicycloid traced by the point on the circumference of the smaller circle, so that's this flowery looking thing, is given by these two parametric equations as shown in the figure below. Find the arc length of the epicycloid. Okay? So what we have is, you can't see it, but there is a circle of radius 5 all the way around the outside of this. And there's a tiny circle on the inside rolling along. Okay? Now, anytime you see a shape that has symmetry, always look to see if you can cut it down and make your integral as small as possible. How many different pieces here that are the same size do you see? I see 4. So if we can cut it down to where we're going to find the arc length of one of them and then quadruple it, we've got the whole thing. Do you agree with me? Because it goes top and bottom, you can't just do an integral all the way around a circle. It just doesn't work that way. You have to do each one individually, or do what we were talking about, do a section and then multiply it by a factor of how many it is. Yes, ma'am?
What does that look if it's going to be like positive or negative?
It's a length of an arc, so it's always positive because it's distance. Yes. Okay? So we're going to do the quadrant 1 section. But first, we need to take the derivative. So dx dt, right here at the top. What is the derivative of 5 sine of t? 5 cosine t. Minus, what is the derivative of sine of 5t? It is 5 cosine 5t. Where is that 5 in the front coming from? The inner derivative, the derivative of the inner. Good. Then dy dt is the derivative of the other equation, which would be 5 cosine t's derivative would be negative 5 sine of t, because the derivative of cosine is negative sine, And then this one will turn positive 5 sine 5t. Agreed? So we're going to be squaring the dx dt, squaring the dy dt, putting it in a integral, and it's 4 times the integral. Okay, we'll come back to the limits of integration in a minute. So let's set up our radical. We're going to have 5 cosine t minus 5 cosine 5t squared plus negative 5 sine t plus 5 sine 5t squared dt. And I'll give you a second to write all that down. Are we ready to go?
Yes.
Okay. What we're going to look at is these 4 points. We're going to do quadrant 1. All right? So, what do you notice is happening at each of these points on the axes?
They approach certain.
What do you call that thing when the graph comes together like this? You remember? It's called a cusp. Y'all remember a cusp? Okay. A cusp is a point where the derivative fails. Okay? So these cusp points are where dx dt and dy dt both equal 0 at the same time. Okay? And that happens to occur, dx dt and dy dt both equal 0. It happens to occur at 0. If you plug 0 into dy dt, this will be 0 and 0. Do you agree with that? If you plug it in here, cosine of 0 is 1. So that would be 5 minus 5, which is 0 also. Okay? So this happens to be at t equals 0. And I'm not going to go through all the math of it, but you could go test it yourself. It also is at every quadrantal angle. So it would be at pi over 2, and at pi, and at 3 pi over 2. So those are basically the t values where it cusps every time as you go around the circle. Okay? It really doesn't matter which 2 we pick, provided that they're consecutive. Because I don't care where they start. If this happens to be where t is 0 and this happens to be where t is pi over 2, I'm going to get the same length as if this was where t is 0 and this is where t is pi over 2. Do you agree with me? Because it's basically 0, pi over 2, pi, and 3 pi over 2. It's kind of like going around the circle with an angle. So we're going to use the limits of integration of 0 to pi over 2. I could use any 2 of those I wanted to if they were consecutive. I could do pi over 2 to pi, or pi to 3 pi over 2 if I wanted to. But I'm going to use the simplest ones I can. Okay? So those are my limits of integration. So now I'm going to plug it in the calculator. And this is kind of a yucky one. So here we go. Math 9. Oops, I forgot my 4. 4, math 9. 0, and then pi over 2. So we have square root, parentheses, 5 cosine t minus 5 cosine 5t, close, twice, and square, plus negative 5 sine t, close, plus 5 sine 5t, close, twice, squared dt. And it should come out to a nice pretty number. Yeah. Oh, something got typed in wrong. Do I have a double parentheses in there? Let's try it. Second. Oh, I forgot one here. Yeah, I forgot one. I put one in the wrong place and forgot another one. So we insert a parentheses there. That's why it was taking so long. There we go. It was all confused. There we go. It's big fat 40. Are y'all getting 40? L equals 40. Any questions? Yes, sir.
Can you explain the pi over 2 part for the constant integration?
Okay. So, because each of the points where the pieces stop is a cusp,
Oh, and then,
their dx dt and dy dt are undefined, or they're both 0. It's a 0 over 0 situation.
Oh, that's one part.
So, yes. Uh-huh.
Oh, okay, now I get it.
Okay. Other questions? Yes, sir.
So will they always give us the circumference of a small circle given like x and y?
They will always give you the x and y, the parametric equations, yes. Yes. Okay? Any other questions? Are we ready to move on? Question?
Like regarding a problem like this, would they ever like ask us to find the circumference of one of these?
No, no, no. I don't believe so. Okay, the last question we're going to do is number 8. And number 8 says a bicycle race course is in the shape of a spiral whose parametric equations are given by these equations right here, where x and y are measured in miles as shown below. The race starts at the origin, does 3 spiral revolutions, and then goes back to the start. So there's another piece that we're going to measure going that way. We have to go back to where we started. What's the distance the bikers ride? How long of a bike race is this? That doesn't look like a fun racetrack to me, but that's okay. So we are doing length of a curve in disguise. It doesn't come right out and say what's the length of the curve. We want to find the length of the curve. So we need to take dx dt and dy dt first. Now, that equation for x, I believe, is rather scary. T over pi. Ooh, T over pi. Ugh. Okay, do me a favor. I want you in your brain to change the pi to a 2. T over 2, okay? That's not quite as scary. What is the derivative of t over 2?
1 over.
It's just 1/2, because t over 2 is the same thing as 1/2 t. Think about it. You just slide the t off the top and you have 1/2, and the derivative of 1/2 t is 1/2. Do you agree with me?
Yes.
So what is the derivative of t over pi? 1 over pi. But before I go taking any derivatives, the answer is not 1 over pi times negative sine of t. Why not?
Because it's you get to do the 1d2 plus 2d1.
You have to do 1d2 plus 2d1, which is also known as the product rule. We have 2 t's here. So we got to do product rule. So 1 is t over pi times d2. What's the derivative of cosine? Negative sine. Negative sine of t, 1d2, plus 2, which is cosine of t, d1. Now, what did we just say the derivative of that was? 1 over pi. Okay? Now, since the whole thing is really over pi, I'm going to write it as 1 big fraction over pi, and it's going to make it easier to put in the calculator. So the first term is negative t sine t plus cosine of t. And there is my derivative. Take a look at it and see if you follow. dy dt, same process. We have 2 t's, so we got to do product rule again. So 1 is t over pi. d2 is cosine of t plus 2 sine of t times d1, which is 1 over pi again. We're going to write 1 big fraction one more time. So pi is the denominator, and I have t cosine t plus sine t. So there's my dy dt. So let's put it into the integral. So L equals integral. We'll talk about limits of integration after we set it up. Big square root. So we have negative t sine t plus cosine of t over pi squared plus t cosine of t plus sine of t over pi, the quantity squared, dt.
You know, like how you change it into the fraction parts?
Mm-hmm.
So I know it's, okay, so it's negative t sine t because you multiply the t times the sine, right?
Yes.
And then, how come, like what happens to the 1 over pi?
I multiplied the cosine times 1,
Yeah. And then the pi goes on the bottom.
and the pi goes on the bottom.
So then what about the original pi? So why isn't it like...
This is a pi underneath both of them, so I made it into all one fraction. There's one fraction. There's the other fraction. You see it? Okay. Okay? Now, we need limits of integration. Okay, there is a key in the problem that tells us what they will be. There is a number we haven't talked about yet. What number have we not talked about? 3 spiral revolutions. How many? It's not how far it goes out, it's how many times it takes to go around. T is measuring time this time, or it's also measuring radians. So how many radians is 3 spirals? 3 times 2 pi. 2 pi is once around, right? So it's 3 times around, so it would be from 0 to 6 pi. 3 spiral revolutions is 6 pi. Okay, so do you remember how to put the fraction bar in the calculator?
Yeah, alpha
Alpha y equals an enter. So we end up with 57.206 if you round. But that's not the answer.
Oh, you have to do the length of plus 6.
Plus 6. Where are you getting the 6 from again?
The line going back to the order.
The line going back to start, because it says he does 3 spirals and then goes back to start. So it's 6 units long to go back to start. So that means my answer is 63.206 miles. That is a long bike ride. Yes, sir.
Parametric equations are given. Like, it takes into account that each spiral is 1 inch.
Yes, that's the T over pi aspect of it.
So we don't have to worry about that.
Correct. It takes care of it itself. Okay? Yes, sir.
I know that we added 6 because it comes back to the x-axis at 6.
Yes.
But I was wondering what's that 6 represent?
Okay, it tells us that the race starts at the origin, makes 3 spirals, which ends here, and it's not the fact that it ends at 6, it's the fact that it takes 6 units to get back to 0, because then it says it goes back to start. This is the 6 right here, how long that is. Okay?
Okay, the distance between where it lands
And where, at the beginning, you have to go back to the starting line. Are we good? All right. We are not doing the rest of this page because it talks about a topic called surface area of revolution, which is not part of the BC curriculum. We have enough to do as it is, and that is all for today.